Hello, sir.
Good afternoon, Junaid.
Good afternoon.
Good afternoon, Toluwani. Good afternoon, Ling.
Hi.
Hello, welcome. Good afternoon, Eunice. Do you have any questions from last time or any things you'd like me to go over? Or shall I move on? Can move on. I need to remember to look up because you're here virtually instead of down where the screens are. Okay. So as I mentioned last time, we have now I've covered the very introductory material, which is these affine maps. Right? Affine maps are maps with constant derivative. We have seen basically three kinds of affine maps. They're very closely related. The maps on the real line, just given by where the graph is just a straight line, the affine maps on the real line. And then two very interesting classes of maps obtained just by taking the same family of affine maps, but mod 1, which means that we look on the circle, and we get rotations, circle rotations, rational and irrational circle rotations, and we get uniformly expanding maps of the circle like 10x mod 1 or 2x mod 1. Now, as I said last time, these are really, in some sense, the first fundamental examples that you would always refer to. But now we want to start a little bit more systematic study of more general systems. And there are many different ways in which to organize dynamical systems. For the purpose of this course, I want to organize them according to the dimension of the space. So these maps that we have looked at so far are dynamical systems on a one-dimensional space, either the real line or the circle. Things get, even in one dimension, things can get significantly more complicated. They get even more complicated in 2 dimensions or in higher dimensions. But remarkably, there's also a very interesting class of dynamical system on a space which we can think of as a 0-dimensional space. So this is going to be what we're going to start with today. I'm going to introduce a 0-dimensional space on which there's some very interesting dynamics already. So we're going to start with, let's say, 0-dimensional dynamics. So why do we call it 0-dimensional? I think this is interesting also because it introduces a more general abstract space, a metric space. As I've said several times before, we've been looking at examples on the circle or the real line, but when I make definitions on general metric spaces. So this is a somewhat more abstract metric space, and so it will be useful to develop, but it's, on the other hand, it's an explicit example of an abstract metric space, so it will be useful to understand better some of the concepts that we have introduced. So how do we define our set? We define it like this. First of all, we fix an integer L greater than or equal to 2. And then we introduce just the space A, which is just the space of L symbols, 0, 1, up to L minus 1. So for example, if L is equal to 2, this is just 2 symbols, 0 and 1. If L is equal to 10, then this is just the digits 0 to 9. As we shall see, this abstract space is closely related, although different in some very fundamental ways, from our usual decimal and other base expansion of real numbers. And then we're going to define a set sigma plus L, which is by definition equals the set of sequences, the set of infinite sequences where each term of the sequence belongs to the set A. Okay, so this is the collection of all infinite sequences, right? The elements of this set are the infinite sequences on this, where each element of the sequence belongs to one of this. So for example, if L, let's choose L equals 3. It's a very natural choice. And then we take A is just 0, 1, and 2. Okay, so every sequence is an infinite sequence of 0, 1s, and 2s. So for example, we have X bar may be equal to 2, 0, 1, 1, 2, 0, 0, 2, 1, 1, whatever. Okay, this is an infinite sequence. So this is just a set. As you know, I'm going to define now, between this lecture and probably also the next lecture, I'm going to define two dynamical systems on this set. Okay? I'm going to define two maps on this set. And then we're going to study the dynamics of the map on this set of sequences. And as you remember, to study the dynamics, it's very limited what we can do unless we introduce some kind of metric or some kind of topology on a set, right? We can, if we have a dynamics, if we have a map, we can say fixed points or periodic points we can determine, but beyond periodic points, you really need some kind of metric, right? Because you want to look at the limit points of the orbit, okay? The sequence given by the orbit, which is a sequence in the space of sequences. This will not be as confusing as it may seem at the moment. So we want to define a metric on this space. So we want to define a metric on sigma . So before I give you the definition of the metric, intuitively, what do you think, when do you think that two sequences intuitively should be considered to be close to each other? In a natural metric, in this space, the space of all sequences.
The infinite metric, supremum of xj minus yj modulus, maybe.
Okay, that's a very interesting suggestion. So there is a very natural metric, which is the discrete metric, which is the metric between two sequences x bar and y bar is equal to the supremum over I of xi minus yi. Is this what you're saying, Milmokshin?
Yes, yes.
Yes. Very good. So what kind of space do we get with this metric? What is the distance? What is the possible distance between two sequences?
From 0 to L minus 2. No, L minus 1, yes.
From 0 to?
L minus 1.
L minus 1, right. So what is the minimum distance between 2 points in this metric?
1 if they doesn't coincide.
Exactly. So the distance between these 2 points, any 2 points, is either 0 if they are the same point. Of course, that's part of the definition of a metric. If these two sequences are not the same, then the distance is at least 1. Right? So this is a perfectly reasonable metric, but if you think about it, it does not promise to be very interesting from a dynamical point of view, right? Because we will never be able to have any sequence of points in this space that is converging or accumulating on any other point, because the distance between any 2 points is at least 1. So you can never have a sequence of points. This space does not have any accumulation points with this
Then we
metric.
can introduce new metric by series. Just xi minus yi over 2n, maybe it's some convergence sequence, and we can get some infinite sum.
That's right. That is now a more interesting suggestion. So both of them are good. So we can define another metric, x bar, y bar, which is, for example, this. Actually, I wanted, before I write down the metric, I just wanted a little bit more to discuss from an intuitive point of view, right? Because this is very formal. We introduced this metric. So from the point of view of this metric, 2 sequences are never close to each other, right? So we're really looking for a metric in which somehow you will be able to have some sequences that are arbitrarily close to each other. So if I give you 2 sequences, what would you imagine would be another sequence that is close to this one, for example? If I want to define another sequence y, and I tell you, okay, we've not defined the metric yet, so I cannot ask you as a formal statement. But if I write down another sequence, what kind of sequence do you expect to see to say, well, yes, that is almost the same sequence?
Which eventually become equal to it.
Okay, that is a very interesting suggestion also. It will eventually become equal to it. So suppose I write a sequence that is 1, 1, 0, 2, 1, okay, 0. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then from here on, okay, from here on, this sequence is always the same, right? So the only part where it changes is this sequence. This part, the first part of the sequence is different. So would you say that these 2 sequences are close or are far apart in the space of sequences?
Close.
Close. How close? So,
It depends on the metric we define.
excuse me?
It will depend on the metric. It is just intuition.
Does anyone have any other suggestions?
Well, I would say if the digits are all the same up to a certain point.
Up to a certain point, Ulwani. That's a very interesting alternative. So we have 2 possibilities, right? One option is that the digits are eventually the same, okay? And what Toluwan is saying is the opposite, is that we take 2 sequences that begin with the same digits, right? So this is 2, 1, 1, 1. And then we take y bar is equal to 2, 0, 1, 1, 2. And then maybe you have something different here, right? So here we have that these are the same. Which of these 2 seems more solid? And to tell you the truth, I am not sure that I can say right now what is the problem with this particular approach, except the fact that I'm not sure that we can define a metric. If I thought about it, I could probably explain why, but I don't think that we can define a metric that has this property where two sequences are the same if they are close, if they're eventually the same. Right? On the other hand, it is very easy to define a metric where two sequences are very close if the first 100 digits are the same. If you think about it, this is very consistent with our intuition with the usual decimal expansion, for example. Right? If we have two digits and their decimal expansion coincide for the first 100 digits, if we have two numbers, right, and they coincide for the first 100 decimal places, then they're extremely close. Right? It doesn't matter what happens after the 100 decimal place. Whereas if they're different in the first decimal place, then they are far apart, 0.5 something and 0.7 something. It doesn't matter really if after the fifth decimal place they're all the same, but one starts with 0.5, one with 0.7. This is not to say, to be honest, I've not thought exactly as to whether it's possible to have a consistent metric of this kind, but the metric that is useful for us is one that follows this kind of intuition, and as Milmukshin says, it turns out that you can write it exactly like he said, so we can write the sum between 0 and infinity of xi minus yi over 2 to the I. And you can see, if you think a little bit about what this is measuring, you can see that this gives a lot of weight to the initial digits, right? Because, sorry, when I equals 1, because I'm taking here from 1. So this is x1 minus y1 over 2 plus x2 minus y2 over 4, right? Plus, let's write 2 squared plus x3 minus y3 over 2 cubed, and so on. So you can see that if the first 3 digits even are the same, then these terms will be 0, right? So if xi equals yi for, let's say, y less than or equal to 3, for example, then this means that the distance between x bar and y bar will be equal to the sum from I equals 4 to infinity of xi minus yi over 2 to the I.
Why can't we divide by L instead?
We can.
It would be like as if it's 0, 1, the interval 0, 1 written in base L.
Yes, this is a very good question, Yunus. In fact, one of the exercises is to show that we can divide in base L if we want. It's the same. It gives the same topology. We can use 2, we can use L. In fact, L is very natural. I will make a comment about that in a few minutes, okay? L is a very natural choice for a reason that I will discuss in a few minutes. But 2 works also, okay? Because it gives a converging sequence, so this always converges, and that's all you really need to define the distance, okay? So this, of course, is less than or equal to something. So this is small. This is less than or equal to something that is relatively small, if you know, from 4. And so the longer, the more terms that you have equal to 0. And of course, the tail of the sum will be uniformly bounded by this. I guess this we can write as less than or equal to I from 4 to infinity of this. The maximum of this is L over 2 to the I. So this is less than L times 2 to the minus 3 maybe, something like that. Okay, so we have this kind of bound here. Okay, so this is actually a metric. So there is without even wanting to introduce a metric, for those of you who know about product topology, if you take the discrete metric on this, just a small remark, and you take the topology, the product topology on this, because this can also be written as a product space, which is a to the n. Okay, this is not so important for what we will do, so if you're not so comfortable with the idea of a product topology, but if you are, this is just the product topology, because this is just n copies of A. In each place, you choose one point of A. There's a product, so you have the discrete topology here, you have the product topology over AN, and the product topology is metrizable with a metric like this. Okay, there's also some other equivalent metrics in the exercises. I will give you another equivalent metric that is sometimes used that induces the same topology that is sometimes useful, but we will generally work with this metric here. So you can see in this metric, again, I will give you in the exercises that x and y are close intuitively if and only if they coincide for the large number of initial digits. So what is the topology of this space? You know, when you have a topological space, you can describe certain topological features of this space. For example, if it's connected, if it's compact, if it has isolated points. With this metric, this becomes a topological space in which every point is isolated. Right? Isolated means there's no other points that accumulate that come arbitrarily close to this point. What is the topology of this space? Any ideas? Do you think it is connected? Remember what connected means?
There's no separation.
There's no separation. That's what connected means. So connected means that you cannot write your set as a union of two open sets. Right? If you can write your set as a union of two open sets, it's not connected. For example, if you take an interval in the real line, it is connected because you cannot write it as the union of two open sets. Right? If you chop this interval in half, then you need to decide what to do with that point in a half, and either you join it to one interval on the other, and then one of the two intervals cannot be open. Right? So what is this structure of this set with this metric? So, yes? So this has the following properties. So first of all, it is uncountable set. Is it countable or uncountable set as a set of points?
Really uncountable.
It is uncountable, right? You
Yes.
can prove it by Cantor's diagonal argument. If you're not familiar with it, I will put it in the exercises. It's very easy. It's exactly the same way that you prove that the real numbers are uncountable. Right? So it's uncountable. This is not a topological property, but let's add it here. It is compact.
As a product of compact sets.
Exactly. So this can be proved either because there's an abstract theorem that says that the product of compact sets is always compact. In fact, yes. It is fairly easy to show also that it is sequentially compact. You can show, in other words, that every sequence has a converging subsequence. We can show it directly by hand in this case. It is totally disconnected. What does totally disconnected mean?
Singletons are connected components.
Exactly. There's no connected components that are not just singletons, single points. So that means that it's an uncountable set, but you can keep breaking it down as unions of open sets until you get down to individual points. Right?
Counter-like set then, that one.
Excuse me?
Counter-like set. It's
very good. There's one more property that we need, which is that it is perfect. So perfect means that it has no isolated points. Every point is a limit point of other points in the set. So a topological space that has exactly these properties is called exactly a Cantor set. Right? A Cantor set. So not just Cantor-like set, because it is actually a Cantor set. So the usual Cantor set that probably you're used to is when you take the middle third Cantor set, like you construct a specific Cantor set. But in fact, the term Cantor set generally refers to a topological space that is compact, totally disconnected, and has no isolated points and is uncountable. Exactly these properties here. All the Cantor sets are homomorphic to each other, so there is only really one Cantor set. That's why we can say that this is a Cantor set. A Cantor set is a word that we use to describe a topological space with exactly these features here. Okay. So I will not prove this here. I will give some, in the exercise, I will ask you to prove that it's uncountable and some of these features here. What I want to do now, before we introduce the dynamics, just say a little bit more about the structure of this topology, the structure of this as a topological space. And notice that we have some very, we can define a basis of the topology in the following way, which is very interesting. Let me write it here. It will also help to understand why it's totally disconnected, actually, if we write it like this. So, so let's choose, for the sake of explaining these ideas, let me choose a specific value of L because it's a bit easier, but you will see clearly the definitions work easily for every L. So let me choose L equals 3, just so that it's not 2 and it's not much bigger. And let me define, so we have the set sigma. So we have A, okay, I've already chose that actually. And then we have sigma phi plus is equal to A to the n. And then let us define C0 is equal to the set of sequences in sigma 3 plus such that x1 equals 0. So this is simply the set of all sequences that start with 0. Very simple. C1 is equal to the set of sequences that start with 1, and C2 equals the set of sequences that start with 2. So I think it is easy to see that sigma 3 plus is just the union of this. Exactly, right? The disjoint union. These are disjoint subsets because this is all the sequences that start with 0, start with 1, start with 2. So they're disjoint. And every sequence clearly either starts with 0 or 1 or 2. So this is exactly the union of these. Now, are these open subsets of sigma 3 plus?
No, it's what kernel of some continuous function, so it's closed set.
And so if it's closed, does it mean it cannot be open? So if all 3 sets are closed,
Yes, it may be open closed set. It's simply.
this is an interesting observation, right? So in fact, so Milmukshin always has very sophisticated ways to get to the answer, which is good, Milmukshin. But so your argument is that each of these is closed, and as you know, the complement of the closed set is open, right? So if each of these is closed, the union of 2 of them is closed. So each one of them is the complement of this union, so it's also open, right? On the other hand, it's also easy, and I will leave this as an exercise, and I would like to do this directly, to show that it's open just using the metric, right? You take a point in here, you take a sequence in here, and you show that there is a neighborhood in this metric of sequences which must belong here. Which, if you think about it, is very easy because the distance, all these sequences, they start with 0, all these start with 1, all these start with 2. So all these points are kind of, in some sense, separated from each other, okay? I will leave that as an exercise for you to think about. But now I want to continue on the basis that each of these is open, which is already a way to show that this is not connected, right? Because we have written this as a union of open sets. And now we can, each of C0 is also not connected, right? How can we write this in a natural way as a union of open sets?
S00, C01, C02.
Exactly. So we can write C00 is by definition the sequences in sigma A plus such that x1 equals 0 and x2 equals 0. And C01 is equal to the same, right? So x1 equals 0, x2 equals 1, and C02 is equal to the same, where x1 equals 0, x2 equals 2. And then in exactly the same way, you can show that these are also open and closed sets. So one of the characteristics of the Cantor set is that there's lots of open and closed sets because it's totally disconnected because of the features of the Cantor sets. And here you can see it directly, right? You can see that each of these is open, which means the complement is closed, okay? So all of these are open and closed sets. The same here, these are open and closed sets. You can see clearly that the union of these is equal to this. So C0 is equal to the union of C00, C01 union C02, okay? And then, of course, it's clear that you can keep going, right? So we can write, so let me go back to the beginning here. So for any finite sequence A1, A2 to AN with AI belonging to our alphabet A, we let C A1 to AN to be, by definition, the set of sequences X in sigma phi plus. Or let me now define it in general, right, for L. So now we'll make a general definition. So for any sequence, you take this such that x1 equals a1, x2 equals a2, and so on up to xn equals an. This is called a cylinder. This is sometimes called a cylinder of order n. Sometimes thought of this. This is an open set, as we just said. Notice that we have nested. These sets are nested, right? So if we have C A1 to AN is contained in what cylinder set of order n minus 1?
We dropped one of them.
A1
Up
to
to an minus 1.
AN minus 1, right? Because this is the set of sequences where you fix the first n iteration, first n digits, and of course this is contained in the cylinder set of order n minus 1, where you fix just the first n minus 1, and this is contained, and so on, and this is contained in C A1. Right? And so if we take if we choose a sequence A bar in sigma plus L, and then we take the nested intersection of the cylinders A1 to AN for n greater than or equal to 1, what do we get? So we take CA1, and then we take the cylinder CA1A2, which is contained in it. These are all nested, CA1 to AN, and then this will be contained in CA1 to AN plus 1, right? And we continue. This will clearly contain the point A, right? This sequence A by A, I'm supposing that this is A1, A2, A3, and so on, right?
No, it's singleton. It's equal to this single set.
Why is it equality? How can we prove that it's equality?
Let's calculate diameter of each of these nested sets, diameter of these sets.
Does everyone agree with that? What is Milmukshin case? What is he saying about the diameter of these sets? So it's true that with respect to our metric, these cylinder sets have smaller and smaller diameter, right? Because here, all the sequences in this cylinder set, they coincide for the first n digits, right? The first n digits are the same. So according to the metric, remember, all the sequences in here, they're all very close to each other. And the bigger we take n, these cylinder sets not only are nested, but their diameter is going to 0. That's true. So you would expect that if the diameter is going to 0, then there can only be one point in the nested infinite countable intersection of these points, which is true.
More precisely, diameter is 1 over 2n.
What do you mean by the diameter? Okay.
Yes, so the diameter, that's a very good question, Toluwani. What do we mean by diameter? So the diameter of a set is the maximum distance between any 2 points in the set. Okay, so the diameter, usually we think of diameter in a circle, but the general, often in a metric space, you say the diameter of a subset of the metric space, or the metric space itself, is just the maximum distance between 2 points. So when we say that the diameter here is bounded, is small, is because if you take any 2 points in here, you know, the distance between them will change, of course, but the maximum distance between any 2 points in here is small. If you take n very big, this is shrinking. But there's also a more immediate way in which we can see that this is equal without using the diameter. How do we know that for sure there can be no other point in here? Suppose there was some other B that belonged to this intersection.
Okay. Consider finite intersection. Finite intersection, then the first some digits is coincides with A by the definition of these sets. Then distance is less than some small number. First we consider finite intersection. B also belongs to finite intersections. Then by definition of these sets, distance from B to A is less than some small number.
Yes, but that's true. But that's basically the same as saying that the diameter is going to 0. There is a kind of way that does not even need to use the metric, actually. Why do we know without even using the metric?
Introduced with topology or metric convergence.
No topology, no metric, just the definition of these sets. The definition of this nested intersection does not need any topology. How can I show that this nested intersection contains a single point without using any metric or any topology? Just set theory, just sets. And the definitions.
Equality or containing? Which one? Equality?
So the fact that it's contained is obvious, right? Because it's clearly contained in these cylinder sets, because each of these cylinder sets is the set of sequences that starts with A up to AN, right? So it's clearly contained. What we want to show is that there's no other point inside this nested intersection. Or rather, we want to show that if there is another point, then this point has to be A. Okay, I will leave this as an exercise. It's a very simple exercise, actually. It's because, of course, if this point was different from A, then at some point, some digit would be different from AN. At some point, some digit BN would be different from AN, and therefore B bar would not belong to the nested intersection, would not belong to C A1 to AN. Right? So all these reasons are good.
Sorry, can you explain again?
Well, suppose by contradiction that there has existed another point in here, right? Then we would have that B dot would be equal to some B1, B2, B3, Bn, and so on, right? But B dot must belong to CA1 to AN, right? So this means that B1 must be equal to A1, B2 must be equal to A2, B3 must be equal to A3, up to time n, right? Because if these up to time n, if they're not the same, then B would not belong to this set, because this is precisely the cylinder set of all the sequences whose first n digits start with A1 to AN. Right?
Okay.
And since it must belong to every cylinder set for every AN, then it means that all its digits must be the same as AN. So B bar must be A bar. It must have all the same digits. Otherwise, it would, at some point, it would fail to be contained in the corresponding cylinder set, because this cylinder set is the sequence of cylinder sets that is defined exactly by this sequence, right? We fix this sequence A, we choose this particular sequence here. This is a particular sequence, right? So any other point, sooner or later, will fail to belong to this cylinder set, because this cylinder set is shrinking, not geometrically, but symbolically, it's shrinking towards A, right? Because when n is very big, it contains all the sequences that coincide up to 1 million iterates. And at some point, the sequence B must be different. Otherwise, B is not different from A. And at that point, if B bar is different at the 1 millionth position, right? When you define the cylinder set that goes up to 1 million, then here it will have a different digits, and so B bar will not belong to that cylinder set, and so it cannot belong to the nested intersection. Is that okay?
Yeah.
Okay, so let's take maybe a 5-minute break. This is, I wanted to introduce the space, the symbolic space as a topological space, understand, get a little bit of feeling for the metric on the space. And let's just take a 5-minute break, get a drink of water, and then we will introduce the first dynamical system on this space and study it a little bit. Okay?
I'm sorry, I have a quick question. Sorry.
Yes.
Is the space complete?
Yes, because it is compact, so it is complete. Yes. So it is sequentially compact, so every sequence has a converging subsequence. So it is complete. It is a Cantor set is like the perfect, it's called perfect, but it's kind of the perfect space. In fact, it's much more flexible than an interval in many ways, you know, because of this being totally disconnected. That's part of the reason why this dynamical system, as we shall see, the dynamical system on this symbolic space they will not just be for the sake of themselves, but they will be used also to study many other dynamical systems will be modeled by this space, because you can do a lot of stuff with this Cantor set. It has all the advantages of any other topological space, and it doesn't have any of the disadvantages. It being perfect, no isolated points, totally disconnected, so you have all these open and closed sets. It makes it a very useful space to work with, as we shall see.
One comment about our name, zero-dimensional. We know that Cantor set is not zero-dimensional set. It's Hausdorff dimension, I think, logarithm 2 over logarithm 3. It's not zero, it's in the interval, in the 0-1 interval.
You're right. In terms of the Hausdorff dimensions, so you're right. Sometimes there's something called a kind of topological dimension, which is 0, which the topological dimension is a kind of just an integer, but you're right. So you can define, for those of you who know what the Hausdorff measure and Hausdorff dimension are. This has non-zero Hausdorff dimension that depends on the exact metric that you use, right? So the dimension, if you just look at this with the product topology, then it's not, you cannot really define the Hausdorff dimension, but if once you fix a particular metric, you can define, you can measure, you can kind of calculate the Hausdorff dimension of that set. In the case of the middle third Cantor set, you have a certain dimension like what Mirmokshin is saying, but in this case, it depends on the exact metric that you choose, right? So if you use 2 to the I or L to the I, you get different Hausdorff dimension for this. So you're right, I use zero dimensional just as a kind of broad category to indicate the fact that it's a kind of totally disconnected set, okay, intuitively. Technically speaking, I should be more precise, you're right. Actually, I realized that I promised Eunice a comment about L to the I, so I'm sorry, why don't I just take 5 more minutes to make this comment. The thing is, I don't want this to make things confusing, so this will just be kind of remark.
No, I asked it because I thought it would be the same thing as the interval 0, 1 written in the, which is not the case since it's a Cantor set.
Exactly, but I do want to make you brought up an interesting point, so I do want to make an observation about this. In fact, I will give a kind of optional exercise, because this is not, strictly speaking, something that I want you to spend too much time with. But let me just make this comment for 5 minutes, a little parenthesis. Let's take, for simplicity, sigma 10 plus, right? Because this is again, more familiar because we think of the decimal expansion. And let's take the metric as Eunice is suggesting. Let's take this metric to be the sum I equals 1 to infinity of xi minus yi over 10 to the I. So Eunice, the point you brought up is interesting, because the question is this the Euclidean metric on the interval or not?
No, this is, this is.
So what does the Euclidean metric on the interval look like?
If it was the absolute value would be on everything on the sum.
Exactly. Very good, very good. So the Euclidean metric, let me write it like this. We could define like this. So this is not the Euclidean metric because this is not the Euclidean space. But what do we get if we write, as you say, do we get a metric on the space? Is this a metric on the space?
I think so, yeah.
No,
It's a different topology, no?
no, it's not metric. Because we have what, 9999 and 1000, it's the same in this topology, in the second metric. If it's called metric, it's quasi-metric.
That is correct. That is correct. Okay, that is a very interesting point. That's why this is interesting. So in this case, if you take x bar equals 0, 9999 repeating, and if you take y equals 1, 0, 0, 0 repeating, then you can check that the distance between these 2 points is 0, because you will have here, because you don't have an absolute value here, so the sign comes in, right? So here you will have, for the first term, you will have -1 over 10 plus the infinite sum of 9 over 10 squared, 9 blah, 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 and this infinite sum will exactly cancel that out, right? So you can check this. I left it as an exercise. Then d hat of x bar minus y bar equals 0, even though these two sequences are not the same. This is called a pseudo-metric because it satisfies the other conditions of the metric. It satisfies the triangle inequality. It satisfies the symmetric property, but it doesn't satisfy the property that the distance is 0 if and only if the 2 points are the same. So you can operate a kind of surgery on your space, and you can identify these points.
Will it always be only 2 points?
So I will not go into it in very much detail, but if you want, you can think about it. I find it quite fascinating because, as you know, the decimal expansion of real numbers is not unique. And it's not unique exactly in these cases. Right? So this corresponds exactly to the fact that indeed this is the Euclidean metric, if you want, but it's the Euclidean metric on the interval, right? And the interval is basically the Cantor set when you have glued together a countable number of kind of boundary points for which the distance is 0. So if you take basically the only points where the distance is 0 are the ones where you have infinite zeros and infinite nines after some time, right? You can check that in those cases you get this distance 0, and you can kind of define a space in which you identify all these points, and then when you identify all these points, this becomes a metric on this new space, and this new space is now a connected, it's a compact, connected, perfect set, which is basically an interval, homomorphic to an interval with this metric, okay? So as I said, I don't want, if you find this confusing, don't worry about it. If you're interested in thinking about it a little bit more, I think it's a very, something that is very curious and very intriguing. It was for me when I kind of discovered this, when I realized this. It's a very simple thing. But we shall see also some examples in which you can really see this Cantor set on the line, and then this Cantor set closes up. So we will actually come back to some situations where we will glue together the boundary points of the Cantor set, and we will get an intervals. And this will be interesting. So I think it's worthwhile thinking about this a little bit. Okay, so it's 5 o'clock, so let's just have a 5-minute break, and I'll see you at 5 minutes past 5. Okay? So now that we have defined and got some feeling for this space, which is non-trivial, let's define the first map. And I'm going to define a map called the adding machine. Or sometimes it's called the odometer. So the odometer is what is in the car to count the kilometers, how many kilometers you go, okay? So you will see why it is like this. So the formal definition, so this is a map tau from sigma plus L to sigma plus L. So to give exactly the formal definition, so we have a sequence so the action of tau, the easiest way is just to show you how it works on a specific example, right? And then we'll see how to define it in general. So suppose we start with the sequence all zeros. And then I apply tau. And this is the adding machine. So basically, the operation is just add 1. So I'm going to add 1 to this point here. So the action of tau on the sequence 0, 0, 0 is just to add 1. And then I'm going to add 1 again. So I get 2, 0, 0, 0. Okay? And then I continue until I get to L minus 1, 0, 0, 0. I just add 1 each time, right? So from 0 to 1 to 2 up to L minus 1. And then what happens when I add 1 again? If I add 1 to L minus 1, what is the natural thing to do? Yeah.
Go back to 0.
Sorry?
Increase one digit.
I didn't hear you. Oh, sorry, I don't realize I don't need the mask. Okay.
Back to 0.
Back to 0. But,
With one more digit added.
excuse me?
One more digit added.
Yes, so I don't want this to be periodic, otherwise nothing very interesting will be happen. So actually, I'm going to add 1 and carry. Carry means that if I add 1, just like I do in the decimal digits, then I go to 0, 1, 0, 0, 0. So this is just like adding numbers. It's reflected, right? Usually in the car, or if you have numbers in a car, right? In a car, we have this, you know, the thing with the speed, 20 kilometers per hour, 50 kilometers per hour, yeah, 150. And then here we have the miles, the kilometers, and then we have here 0. We start with 0 when the car is new, right? And then we kept adding here 1, 2, 3, until you get to 9. And then when you get to 9, it becomes 10. Right? And then from 10, it becomes 11, 12, up to 19, and then it becomes 20. Right? And then you keep going. So we're doing exactly the same thing, but instead of writing the numbers to the left and adding 1, this is just because we think of, visually we write the sequences like this, okay? But if you imagine, we could just as well write the sequence going to the left, and we would have exactly this kind of situation. This is called an odometer in the car, right? So if you think of these are the units, these are the tens, these are the hundreds, just exactly, not in terms of decimal places. You think of these as though they were integers, numbers, right? 0, 1, up to 9, and then you get 10, right? And then what's the next number? You just add 1 here, right? And then all the way up to L minus 1, L minus 1, 0. And then what happens? You need to carry twice, right? This is like when you get to 99. When you get to 99, you go back to 0. Here 1, so you carry 1, you add 1 again, and then you get 100 here. Right?
Abacus.
Excuse me?
It's like abacus.
Sorry, I didn't hear what you said, Ling.
It's abacus.
It's like an abacus. It's like
Yeah.
an abacus. So this is 0, 0, 1, 0. And then you keep going like this, right? 1, 0, 1, and so on. Okay? So, so if you start, in this case we started with 0, but if you start with some arbitrary sequence, you just do the same. Suppose you have 2, 1, 3, 0, so on, okay? Then you apply the map tau, and then you add 1, and you get 3, 1, 3, 0, right? And then depending how many digits you have, for example, if L equals 4, if 3 is the maximum digits, then here you carry, so you go to 0, 2, 3, 0, and so on, and then 1, 2, 3, 0. Okay, this is for L equals 4, when the maximum digit is 3. Is that clear, the definition of this map? So this is a map, a well-defined map from sigma plus L to sigma plus L, right? So given any sequence, any infinite sequence, I map to another infinite sequence. What do I do if I have, for example, if my original sequence is always L plus 1, L minus 1? Then apply tau, then what do I get? So this I kind of have to define, okay? So I'm just going to define that this maps to 0. Because otherwise it's not well defined, right? If I have a finite number of L minus 1, then it's fine. So suppose I have L minus 1, and then here I have 0, and then I just add 1, this goes to 0, this goes to 0, this goes to 0, and then I add 1 at the first possible points. But if they're all L minus 1, then I just kind of carry everywhere, and I define the image under this map as 0, 0, 0. So this gives a well-defined map. So the point is, what I'm trying to say is I've now defined in the notes, I give a formal definitions of all the cases, but it's kind of even more difficult than just to see this, that that's what you do. This is the operation add 1 and carry, and this is the map. So we can try to study the dynamics of this map. First of all, let me ask you something about this kind of map. Is this map injective? You think? Can you have 2 points mapping to the same point?
No, I don't think so. I think this is injective.
Yeah, it's clearly injective, because if you see the way we do it, if you start with 2 sequences that are different, you add 1 to both sequences, they cannot map to the same sequence, right? If they're different, you add 1. Is it surjective?
No, 0, 0, 0. It I think never.
Surjective.
Hey,
I think so.
what?
0, 0, 0. We have this, the last definition you gave. L minus 1, L minus 1. Yes.
Yes.
So every point has a pre-image, right? Every sequence has a sequence which it comes from. We can easily define the inverse of this map, right? Because it's just kind of, you can see that. Sorry? I didn't hear you. Okay, so it's easy to check. So you should do this, you should think about this at home. The tau is a bijection. Is it continuous? If you take two nearby sequences, right, suppose you have two sequences, x bar, y bar, that are close, so x1, x2, x3, and so on, y1, y2, y3, and so on. What does it mean that they're close? It means that they're the same up to some n. Right? So we suppose that these two sequences are actually the same up to time n. This means these 2 points are very close. What can you say about the images? Are the images going to be very close?
Yes.
Yes, of course they're going to be very close because you are acting on this point here, you are adding 1. This is the same, this digit is the same digit as this, right? So if you just add 1 to this, in fact, you can check that the distance is going to remain the same. This is in fact an isometry, right? If you take the distance between these 2 points, you just add 1 to both of these, the distance will remain exactly, the distance between the images will be exactly the same as the distance between the points. So if the points are nearby, the images will be nearby. I'm not giving a formal proof because I want you to do that in the exercises, okay? But the lemma is in fact that tau is a homeomorphism. It's a bijection, it's continuous, the inverse is continuous. It's very easy to check directly all of these properties directly from the metric and from the definition of the map. So it's a homeomorphism. So what is the dynamics? That's what we want to know. Do we have any fixed points?
No.
Why do we not have any fixed points?
Because we had one first digit.
That's right, exactly right. So there's no way you can have a fixed point because if you, every time you add 1, you change the first digit. It's never going to be able to stay the same as what we had before, right? So you cannot have any fixed points. It's fairly easy to see that you cannot have any periodic points for the same reason. What happens to the points then? What is the orbit? Remember, once we get beyond fixed points and periodic points, then the natural question we ask is what is the omega limit set of an orbit, right? So what are the limit points? So if the point is not periodic, if there's no fixed points and there's no periodic points, then we have an infinite sequence of points, and the space is compact. So we must have some limit points, some accumulation points. So let's look, for example, at this particular initial condition here. Right? Suppose this is our initial condition, x0, 0. And this is the orbit of tau. This is the orbit under tau of this initial condition of this particular point, 0. So what are going to be the accumulation points of this orbit? Which points is it going to come close to? Arbitrarily close to, right? Remember, it's a limit point if there's a subsequence that converges.
All points?
Every point, why is that?
Because the orbit is the sequences that are eventually 0, and each sequence could be approximated by sequences that are eventually 0.
I agree with the second part of what you said, but not with the first part. So we want to take any arbitrary sequence, and we want to show that it's approximated by this. So let's just take an arbitrary sequence, z bar equals z1, z2, z3. Z4, right? And is it true that the orbit of 0 will, if we wait long enough, come arbitrarily close to this point, whatever this is? This is not necessarily eventually 0, right? This is not eventually 0. This is any point. So what do we need to do? Well, we need to fix an n. And we need to know whether at some point the orbit of 0 will be a sequence whose first n digits coincide exactly with this one. Right? That's the same thing as fixing an epsilon in some sense and saying that you come within epsilon. So will there be some point in the orbit of 0 where the first n digits will be exactly these digits, whatever they are, 5, 6, 1, 0, whatever? Can we guarantee that?
Yes.
Why?
It's finite.
What is finite?
I mean, you can keep adding 1 until you reach Z1 and Z2, Zn.
Exactly.
So n is finite. N is finite, then we can do like this.
Exactly, Ling, right? I think if I understand correctly what you said, if you think of this as a number, finite number, right? Then what you're doing here is you're just basically listing the natural numbers, right? It's very similar to what we discussed the other day. So here you start with 0, you have 1, 2, up to 9. Let's say, let's think of this as L equals 10, just for our intuition. We get to 9, then we have 10. If you look at it backwards, like we have 11, up to 99, right? So here we have, if you look in the first few digits, we have all the possible sequences of length 1, right? And then when we get to the end, we start with the sequences of length 2. And by the time we get to here, we have had all the possible sequences of length 2, right? Because we have 0, 1, 1, 1, 2, 1, 3, 1, and so on, and until we get to 3, 2, and so on until we get to 0 here, and even we include this, 0, 0. Right? And then here we have all the sequences of length 3, and we go through all the sequence of length 3. So eventually we will have any possible sequence of length n will appear. In fact, I know pretty much when it will appear. Is that convincing?
Yes.
It's particularly convincing if you think of your car, right, or your motorbike, and the kilometers on your motorbike. Clearly, if you keep going, you will get any finite number. You just go through 1, 2, 3. As I said, you think of this as really being reflected in the other way. So you think of this as actually being a number where these are the units, right? You think, sorry, these are the units. These are the tens, these are the hundreds, and so on. And then you just add 1 each time and you carry, and you get all possible finite digits. So the sequence of 0 is dense, okay? So the omega limit set of 0 is equal to all of sigma L plus. The omega limit set of 0. What about if we take some other arbitrary initial condition? X naught. What can we say about the omega limit set of that? We still want to, suppose let's try to prove that this is dense also, right? So we want to approximate we still want to approximate the same number. How can we guarantee that some iterate of this point will come close to this? So the first n digits will be exactly these ones here.
I think the term before S0 will not be the limit point.
It will not be what, sorry?
The term before S0
The term before x naught
will not be the limit point.
will not be the what?
The limit point.
The leading point.
Limit point.
The what? Sorry, the sound is not so good here.
Limit point.
The term before x naught will not be a limit point.
I will not be a limit point. Sorry, Ling, what's your statement that z bar will not be a limit point of the orbit of x naught? Is this what you're saying?
So, let's say S0 is 2000, then no, S0, the initial point.
Oh, sorry, yes. So let's suppose that, so let's maybe fix some L, right? What shall we choose for L, just to be a little bit more practical to get a feeling? Shall we choose L equals 10 or shall we choose L equals 3? I think 3 is a good number because it's not 2, but it's not too big, right? So let's suppose x naught. Okay, what do you want x naught to be?
200.
Okay. We apply tau, what do we get?
3 up to L minus 1.
So L is 3, right? So we're already at L minus 1.
Yes.
So we have to carry, so we already
Zero,
get
1.
0, 1, 0, 0, 0.
It's just counting. We can reach any number from h0. We just count from h0 to any number, and Zn the first digit in our counting, in our Zn is the first digit. So we can reach any number by counting. We start counting from h0 and to the number what we want.
Yeah, I think I understand what you're saying, Mokshin, and it's
It's the
basically
same thing as 0, 0, 0.
Why is it the same thing as 0, 0, 0, 0?
Just you have to advance like that number minus x0 times or something. Because that if the number is less than x0, you can take something really big, but after zn plus 1.
Okay, so basically I think, Yunus, what you're saying, and I think this is probably the way to formalize this as best you can, is that if you wait long enough, you will inevitably, you are building up all these numbers, and then at some point you will have n zeros. Because you keep adding and carrying, it's like going to 99 and then to 999. Okay, if I take L equals 10, whatever, and then 9,999, and then at some point you use, from 99 you go to 100, from 999 you go to 1,000, and at some point you will go to a number that just has all zeros up to time n, okay? And then you have some other points on after that. But if you have all zeros up to time n, then it's, as you're saying, Yunus, it's basically like starting from n zeros, and then you just, when you have n zeros, you don't even, nothing happens to the tail of the sequence until you've got to all nines. And as in this some intermediate step between n zeros and n nines, you must hit exactly this number here. Right? Because this number is somewhere between n zeros and n nines. And So you will always get these, you will always get some number that starts with these digits. So it's clear that if you keep, I think all of you are basically expressing the same idea. You need, I think I would like to ask you to put it down to make sure you can formalize that. But I think all of you see that as you add, you can eventually get any initial digits. Okay, so the conclusion of this is that, let's write this as a theorem, is that every, so the omega limit set of the initial condition is equal to x plus L for all initial conditions. So the orbit of every point is dense. So what, we have a name for this. Remember, I introduced the name. When the dynamics, when every point has a dense orbit, do you remember what that's called? So tau is minimal. What is the other example that we saw before of minimal dynamics?
Rotation with irrational.
Irrational circle rotation, right?
Rotations, yes.
Yeah. So notice that there's actually a strong similarity in the two. Even though one is a Cantor set and one is the circle, in both cases, the map is a homeomorphism. It's invertible. It's a homeomorphism. And it's an isometry in both cases. This is not necessary for this, but they're very similar. These are isometries, just like circle rotations are also isometries, right? All the dynamics. So this, for example, does not satisfy sensitive dependence on initial conditions because this is an isometry, so the 2 points stay together. Right? When we looked at the continuity of tau, 2 points stay together, and every point is dense. So this is a very interesting that we can recover in such a simple way dynamical systems that is very similar in its characteristic to a circle rotation, even though it's on a Cantor set. So it's not completely obvious. It would not be obvious a priori how you have a kind of translation, but in some sense it's a kind of translation because any 2 points are just being translated together inside this Cantor set, and they're kind of going round and round in this Cantor set, and they have a dense orbit in this Cantor set. Okay. And in the next week, we will introduce another map on the same space, which instead has sensitive dependence on initial conditions and has the other features. So on this Cantor set, we will be able to define two very different dynamical systems, just like we do on the interval mod 1, on the circle. We defined before the irrational circle rotation and 10x mod 1, and on the Cantor set, we will do a similar thing. Okay. So I will be posting, I guess you noticed that I posted an exercise sheet. So please do the exercises. It's really an essential part of the course to do the exercises. And hand them in through Moodle. I think they can be handed in there. I'm not sure. Can they be handed in directly through Moodle? Is that correct?
Yes.
Yes? Okay. And let me know if you have any questions. I think you had your first tutorial yesterday, is that right?
Yes.
Was everything okay with the tutorial?
Yes, it
Okay.
was okay.
Okay, good. Okay, so thank you very much, everyone. Have a good
Thank you.
weekend. Okay. Bye.
Bye.
Bye.